surface texture. You know, Ed, every surface has a texture.
Yep.
And right now, I'm kind of thankful there's some texture on this stage, so I wouldn't fall and bust my butt and fall off of here. You know.
It has some water retention.
Well,
oil retention.
It definitely has some water retention, or moves some water out of the way. You know, it's funny, I didn't plan it this way, but you know, your bathroom floor also has texture for a reason. So you don't fall and bust your butt, especially if it's wet like this. So everything has texture. The trick is you can actually utilize that texture to create an advantage. And right here on these grounds, there are lots of engines that are actually utilizing surface texture to make a horsepower advantage. And at the end of the talk today, we'll actually show you some of those things. But texture is super important, and the key is you don't want something that's too rough, and you don't want something that's too smooth. You know, that's the real key. It's kind of like Goldilocks and the Three Bears.
That's right.
So if it's really rough, it's going to generate a lot of friction and a lot of wear. If you think about any smooth surface, isn't actually smooth if you look at it under a microscope. There's always peaks and valleys, and if it's really rough, those peaks are really peaky.
Well, yeah, you wear your cylinder out prematurely with those peaks because you're actually getting metal-to-metal contact. And Blake talked just a little bit about where that debris goes.
It goes everywhere. You wish your oil filter would capture all of it, but it doesn't. So when you have a really rough-honed surface like that, all the debris goes everywhere throughout your engine. And if you've got a really high compression, naturally aspirated engine, for example, the reason why piston rings can micro weld to a piston, which seems kind of counterintuitive. How can a steel ring weld itself to aluminum? Because aluminum and steel don't really weld well together. Well, that's because they're actually microscopic pieces of iron embedded in the ringland.
From the cylinder wall.
Absolutely. Which is why you hard anodize them, to make it harder for that debris to impregnate in there.
Yep.
So, but on the flip side, you can also be too smooth. So we get it too rough, that's a bad idea. But you can be too smooth. And I worked at Joe Gibbs Racing, actually when Tony Stewart was there, for 15 years. And one of the things that got us in trouble one time was we started polishing our camshafts. And we were flat tapping back in the day. And as we started to polish that camshaft and make it smoother, the camshafts live longer. We were like, ooh, well, if a little polishing is good,
a lot's better.
And you think, until we showed up at Daytona one year and we blew up every engine we had in practice. And we were like, what the hell happened? Well, the reality was we made it so smooth that it could not hold oil any longer.
Yep.
You know, Ed and I worked together on the Engine Performance Expo. And a couple of years ago, we went visit a company that was a part of that process. And they were making, for an industrial application, I think it was like tractors or something like that.
Yep.
They were making wrist pins. Now, you can DLC coat a wrist pin, and coatings are fantastic, but of course, coatings also cost money, so they didn't want to have the coating. So they had designed this wrist pin, and on paper, it was the perfect wrist pin, you know, for that application, not coated. All the engineers super proud. The only problem was it had to pass a 100-hour durability test.
Yep.
And it would only live 1 hour. And they couldn't figure out what was going on. And we were, visiting the plant, and they were giving the tour around, and I asked them, I said, well, I saw you had those 4 centerless grinders in a row. And one of the production guys put his chest out and said, yes. I said, so tell me, how are you finishing these? He's like, we start off here with 400, then we go to 800, then we go to 1200, then we finish with 1600. And I'm like, okay. Is the stock removal the same each step? Yes. I'm like, that's your problem. He's like, what? I said, you made it too smooth. Then I related to him the story I just told you about Joe Gibbs Racing. I said, skip those intermediate steps. That way you leave some valley to hold some oil. They made that one change, and they instantly could pass that 100-hour durability test. That's a 100-to-1 return right there.
Yep.
Just on changing surface finish. They didn't change heat treat, they didn't change dimension, they changed nothing but the texture, and it made that big of a difference. I know you've seen some of these things with the people you work with on the drag racing side here. What's happened with honing?
Yeah, it's really kind of the same principle.
Right, because really what we're doing is they were using centerless grinders to polish the surface.
Yep.
Old school way was using conventional abrasives, but there's a new school process.
Yep. So we use diamonds in the honing process along with cubic boron nitride, or CBN. And the reason we do that is one for size tolerance, and the other is for longevity. Dollar for dollar, the diamond abrasives will outlast the standard abrasives 8,000 to 1. I mean, it's just incredible, the difference. So we use diamonds, and we use it with a 6-stone hone head to give us the good roundness, because you can have the best finish in the world, but if your cylinder isn't round, I mean, these guys spend an inordinate amount of time making sure their rings are perfectly round. And then if I can't give them a good round cylinder to put the rings in, it means nothing.
Square peg, round hole.
Exactly. Yeah. So anyway, what we try to do is kind of, it's on the same principle that Lake was talking about. We use a rough finish, and we establish a base finish, and then we go over the top of it with a 600 or 800 grit CBN. And what we're doing there is knocking off the peaks and giving the rings a nice smooth area to ride on, but yet we have the valley for the oil retention, because oil is absolutely critical to ring seal.
Oh, it's not just the lubricant, it's also the gasket between the piston ring and the cylinder wall. If you don't have enough oil at the top of that cylinder, it will not seal properly. It's not going to work. You know, in the traditional way of honing, you created this, single process. Peak honing is the technical term, right? And you can see it's jaggy and all that, but what we're really trying to go for is this plateau hone process. Now, Ed, talk about it for a minute, because a lot of people think they have a plateau finish, but they don't.
Yeah. In fact, there's some aftermarket blocks that you'll get. You guys buy an expensive block, and you open it up, and there's directions in there on how to hone it. And it says, you're going to plateau hone. It says, start with a 220 grit, leave a thousandths, go to a 280 grit, leave a half a thousandths, go to a 400 grit. Well, when you do that, you end up with a 400 grit finish. You end up with exactly what you don't want. You have a very fine finish. The rings will initially love it, but there's nowhere for the oil to go. And so your cylinder doesn't last. It'll last half the time or a third of the time that a cylinder with the plateau finish will last.
Oh, the thing about it, my dad raced in NASCAR for 20 years. Like I said, I worked at Joe Gibbs Racing for 15 years. And 20 years ago, when we would get a block together to go race at Daytona, a 500-mile race, you had an 043 3mm ring. And into that 500-mile race, that engine was probably down 5 horsepower.
Yeah. Yes.
Just because it wore out that much. But it was also that single grit, smooth finish like that, because that was all you had to do, right? Try to make it smooth as you possibly could. But today, those guys are running a 0.5 millimeter. That's 020, so that's half the thickness. 2 millimeter ring package. And that same short blocks can run 3. And I heard a couple of guys tell me recently, they're going 4 races now on the same short block, because there's some strategery involved in how they give them seals and have to run so many engines, and it's kind of a game they can play. But you're probably not going to see it super well because of how bright it is right now. But what we're showing here is the transition from a single grit finish, and as you begin to plateau. Like you said, you may use a 170 grit diamond to start, but then you're going to come over with a 600 grit CBN, and it's strokes, not so much stock removal.
Yes, that was what I was going to bring up. Is this Lake, explain to them these little lines right here, okay? How much is one of those little lines?
Well, so each of this whole scale is plus minus 500 micro inches. So that's 1,000 micro inches total. Well, 100 micro inches is a 1/10 of a thousandth. So what you're looking at here, total, is only 1/1000th. Back to what you said in terms of the instructions of how to hone.
Right.
All you're left is a single grit finish. As you can see, now this is, we'll call it maybe a 280 grit or 220 grit finish, and then coming back in with probably, it looks like about a 600, just simulating it. By the time you've removed that 1/2 thousandth, it's all gone.
It's gone. All your value for your oil retention is gone. And remember, a human hair is 3/1000ths of an inch in diameter. So, you can see what kind of tolerances we're working with here. So again, as Lake says, it's not how much you're taking out. In fact, you won't be able to measure the stock removal after you use the 600 grit CBNs to plateau. You'll go back in that cylinder and it'll be the same size as it was before. You're taking so small amount off that you really can't measure it.
And the key for that is because you can't measure it and you can't feel your fingernail, you can't see it with your eyes. We're talking about, 1/10 of thousandths, millionths of an inch removal right here to try to get it right. Because if you don't go far enough, it's not good. If you go too far, it's bad. So how do you know where you're supposed to be? Yeah, that's where you have to be able to measure.
Yes, that's actually the key to this new system or this new process is the ability to measure it. And in the past, we've only had a typical profilometer or surface analyzer that would measure in just like RA, like.
Yeah, and some of the days in the older style ones, we had this skidless, which is really good because skidless can actually measure waviness. But the problem is a skidless profilometer is probably a cheap one now is $8,000. They could go $30,000 and up. Well, that's not really accessible to most engine shops. But fortunately today, a skidded style one, at $2,500, you're in business. And now you can measure things like cylinder heads, decks.
Yeah.
I mean, you can measure everything. Heck, the other day, my wife had me measuring her crochet hooks, right? And it literally could figure out which one worked the best. So you can do all kinds of surfaces with it. Everything has a surface, I said earlier. So the advantage of having this tool to be able to measure is now we can actually see what's happening in that microscopic area.
That's right.
But we're not just done with that. Oh, by the way, one thing when you're doing this stuff is you really have to be clean because what happens when you're, it's a dirty environment, whether you're measuring a engine you just tore down or an engine you just honed. If you're measuring it in the hone, it's going to be dirty.
Yeah, honestly, when you're measuring cylinders like this, you really need to be clean enough to where you would assemble that engine. So it's not just a quick wipe with a rag. It's brake clean and several times and make sure you're completely clean. Otherwise, you end up with, explain that, Blake.
Well, you get a big giant anomaly because the way that skidless works, you get this skid, and then you have the needle that's the tracing along, like the needle on a record. Well, essentially, think about it. If it hits that piece of debris, it's like it skips. Well, then it records it as this big giant dip right here. But in reality, it's not a dip.
Yeah.
It's a bump because you had dirt on the surface. Then it throws all your numbers off. So you're like, well, it said this. Well, that's why you can't just trust the numbers alone, and we'll get into more detail on that in a minute. But that's why it's so important to have it clean. But we also now have microscopes too. So I'll talk about that in a minute, about how this has changed everything.
Yeah, this is a really nice tool to get your crosshatch angle. As I was talking to this gentleman earlier today, we were talking about crosshatch angle. And I'm not smart enough to know what you should use. This is the man that will tell you exactly what crosshatch angle to use. But the camera gives you the ability to check your crosshatch angle throughout the cylinder now. Some of the older machines, you would actually, what would happen is because they changed directions, the crosshatch would flatten out at the top of the cylinder and the bottom of the cylinder. With today's new CNC machines, it's the same crosshatch throughout the cylinder.
And that's a key thing because crosshatch angle is really important because these deep valleys, not only do they hold oil, they also transport the oil. You just mentioned that oil is the gasket. Well, if I have a very long stroke engine and I have a very narrow crosshatch angle, the rings are going to scrape all that oil off, and it's going to run dry. Then you lose your ring seal. So if you think about, say, a Harley engine that's a pretty long stroke, well, there's a reason why they call for that 45 to 60 degree crosshatch angle, is because you need to have that oil transport up and down the cylinder.
You need to have that highway.
Absolutely. Otherwise it'll run out, and run out, bad things happen. So talk a little bit about the variation in what your grit needs to be based on the application and the material you're cutting.
Yep. So again, when we're talking about roughness, this is the key area. This is critical. This is, if I don't make it rough enough, I don't get enough valley for my oil. You can hone all day long and you'll never put any more valley in there unless you go down in your grit size or up in your grit size, depending on what your application is. And the more fuel you put in an engine, okay, typically methanol, or you start putting power adders in it, the combustion pressures go up and it wants to blow the oil or wash the oil off the cylinders. Well, the oil is the sealer. That's what seals the rings. And so you've got to determine what application first. Then what we have to do is determine what type of material. For instance, just a normal passenger car engine's they're pretty soft.
Yes.
And so you might get away with a 170 grit to give you, let's just say, a 70 RVK number, which is our valley depth. If we were to go into a Darton liner, that 170 might end up with a 30 RVK instead of what we were wanting is a 70 RVK. So we have to go to a rougher grit size to put a rougher finish in those harder materials.
Like you said, those are the key considerations, is the hardness of the block or the sleeve you're honing, and the application. You go from, say, gasoline to methanol. For everything else being the same, you're probably going to want to go from, say, an RVK of 50 to an RVK of 75, just because with methanol you're putting twice as much fuel through the cylinder. It's trying to wash all that oil away. And toward the end, we'll actually show you some perfect examples of how much of a difference this can make in terms of the performance of the engine. But like you said, Ed, you got to start with that base finish, because if you don't have it, you can't get it back. So you may have heard some terms like RA, which is roughness average. The cylinder heads, guys have been talking about that for a long time. When we're honing and that base finish, we're not talking about RVK or RPK or RK, any of those numbers. We have to talk about RZ. So RZ is essentially the average of the highest peaks to the lowest valleys. That's your base roughness. And like you said, if you don't have enough, and what I mean by that, so for example, if you want to end up with an RVK of, say, 50 to 60, if your RZ isn't 300 plus, you're never going to get there. If you want to be RVK of 70, then you might want to be an RZ of 400, maybe more, to be able to get there. That's why you want to know, that's why having the profilometer is so important, to be able to measure while you're in process. Because if you just follow a recipe and then measure it afterwards,
it's too late.
Right, you're going to do it again.
Yep.
I hope you didn't go to size, because now you're in real trouble, right? So here's a perfect example. So this was on a Darton liner. So we used a 100 grit diamond to establish that base roughness. Now what's neat about this is everything here is aligned to the lowest valley. So you can kind of see what's happening. So we start off here with a base finish, 100 grit. Then it's just 6 strokes with the 600 grit. And explain plateau mode and why it's so important to change your pressures and how you approach those strokes.
Yep. So a couple of things in some of the newer machines, what you have is you have a operation that we call plateau mode. So typically when you're honing a cylinder, the hone head is spinning and it's going up and down, and the stones are feeding out against the cylinder wall. When we're in the plateau mode, we do not want that hone head expanding until the stroke starts. If it starts expanding and spinning at the top of the cylinder, we end up with a finer surface finish, which is the exact wrong place that you want that finer finish, because that's where it needs the oil, is up there during the combustion, where the combustion happens. So it's real important to have a machine that will actually feed the stones to diameter and then begin the stroke process. The other thing is when you're using the real fine grits, we don't want to apply the pressure that we do to say a 100 grit or a 170 grit diamond. We back the pressure way off. So we're not, if we put too much pressure on it, what can happen is it'll actually round those peaks off instead of hone the peaks off.
Well, the thing too is you can actually take more removal out.
Oh, absolutely.
Quickly.
Yeah.
So if you're normally going with say 40% load in roughing, and if you don't back it down, yeah, you're going to just.
Yeah, that's a good point. Absolutely. Yeah, you'll remove the material way too quickly.
Right. Then over here we've moved from here with the 100 grit really rough. We plateaued it some. It's looking pretty good, but we're not done yet. We want to get a little bit better, get those peaks down, and get it a little bit smoother. So now we came with 9 strokes of the Scotch-Brite, which is a really soft abrasive, which more deburrs that surface. And now you can see how much flatter and smoother that surface is, but it still has valley. And a regular pattern of valley too. That pattern is really key. That it doesn't have just 1 or 2 giant ones. It's consistent.
It's consistent. Yeah.
That's that next level.
We have a real technical term for this. We call it fuzz. It removes the fuzz.
Fuzz buster. I like that. So here's a good example of a cylinder that looks pretty nice. That we've got RVK of 76, RPK, that's a peak of 10, RK of 27, and you look at that curve over there, that one's looking pretty good. That's an example of that dog will hunt, right?
Yep.
So now we're going to get into talk about the numbers a little bit. So that single process finish, everyone's used to, RA, we just talked about RZ, but then when we start really talking about this plateau honing, that's when RPK, RK, RVK, those are the numbers that get thrown all around. And sometimes that can be a little bit confusing.
Well, really confusing.
Well, the other problem is, not are they confusing, because now all these new numbers you're throwing around, they will also lie to you. I know you can't see the screen super well, but all 3 of these have essentially the exact same RA. Yet, as you can see, they're completely different surfaces. I wouldn't want to sit on this one.
No. I don't think I'd want to sit on that one.
No, those are both kind of ugly. So we know we can't utilize RA. That lies to you. So when we plateau hone, we use RPK, RK, and RVK. So Ed, explain a little bit what we're looking at here.
Yep. So this is what we call the material ratio curve. And if you can see this is just that little tail right there. That's actually your peaks. Okay, that's what the ring sees. And when Lake was talking about the Scotch-Brite, if you had a graph of that, you wouldn't see that little tail right there. It would be more flat. And then over here, this is our valley depth. Between here and here is our RK. That's our what we call our core roughness. That's what gives you really, in my opinion, cylinder longevity. In other words, the cylinder's going to last. The flatter that curve, the longer your cylinder's going to last.
So if we go back one slide, what we're looking at here is essentially that 2D drawing, that trace of the surface, where you have a needle on a record, and it's just dragging along, showing you the peaks and the valleys. Well, that's the 2-dimensional look. Over here, this is the 3-dimensional look, where you're actually taking a section of a cylinder and you're looking at it in 3D, and we're scanning it down. So as this moves down, it's moving through the material ratio curve. So up here is air. Everything below that color is metal. That's your block. And this is just that terrain, if you will. So that's what really helps you kind of see.
Absolutely.
This is the valleys that's holding the oil. And these peaks, that's the stuff the ring is going to be knocking out of the way. And again, the more peaks you have, the more debris you have going through your engine.
Yep.
and your engine doesn't like debris.
And Lake, I mean, I've just come across this, or Mark Malberg, of course, our good friend, has shown us this. This has just happened in the last couple of years, this technology.
Oh, this is all super new. Yeah.
Right.
I mean, everything is at the cutting edge. I mean, no surprise here. NHRA Pro Stock is the most advanced and most refined naturally aspirated engines in the world. So obviously working at Total Seal, Matt Hartford having a Pro Stock car, working with the guys at KB and all that, we're actually showing you what we're using over here. When Matt was winning the Indy last year, this is the same technology that's in that car that wins races we're showing you here. Yep. And that's something that's never happened in the past, right? Some people say their kids don't like me telling all this stuff, right? Right, don't share all the secrets, you know? I can't help it. So, we were mentioning that material ratio curve,
yep.
And we thrown out RK, RPK. Ed, explain what each of these mean.
Yeah, so again, RPK, and this is a great slide, because what it does is, as you can see in the blue, is again that RPK, or what the ring sees, and then this is your RK, which is your core roughness, and then the green is actually your RVK, where the oil, and the oil will ride or sit also in the RK somewhat, but.
Yep. So again, back to moving it through. Now you can add in the material ratio curve, and you can see how the material ratio curve changes. As you do that plateau strokes. That's why it's so key. It's like one more stroke can be one too many, right?
And if you notice your material ratio curve, watch how it flattens out as you layer it. You know, once you get to here, obviously you have no oil retention.
And I guess the key takeaway from this is it's better to be maybe a stroke or two too few than a stroke or two too many. Yeah. Because the ring is going to do some of this for you, whether we want it to or not.
The perfect example is, as you were talking about, you know, smooth on the camshaft, and so we picked up horsepower and we kept going smoother. Well, it's the same thing here. You know, 6 strokes with a 600 CBN does not mean 10 strokes is going to be better.
Right, absolutely. So again, here's another example of don't trust the numbers alone. That's why it's so important to have the software. The TraceBall software just makes it easy because it can run the profilometer for you.
You're doing a good job.
And you can plug in the microscope so you can do your crosshatch angle. It just makes it easy to do and get the data you need to make your engine better. And why are we doing all this? Well, we said earlier, oil's the gas. It's what actually seals that piston ring to the cylinder wall. And in the old days, our old cast iron rings, our moly rings, our chrome rings. Oh, here comes the rain. There we go.
Yeah, these are big drops.
Yeah. That's Florida.
I hope your umbrella takes care of your...
Yeah, all right.
All right.
What all three of these have in common is porosity. So the ring itself could hold some oil. But they all didn't really last that long either. With the chrome ring, you had to hone it.
Really rough finish.
To get it to break in. Of course, that generates more
wear
right.
in the cylinder.
With the modern steel rings, we can make the rings lower tension, they can last longer, there can be lower friction, but what they can't do is hold oil.
They can't hold oil.
There's no porosity in any of these down here, which that's the whole reason you have to hone differently. If you've been using moly rings and been the 400 grit following the old Dick Maskin way of doing it, that's fine. That recipe works if you're trying to make chocolate chip cookies.
Yep.
But if you're trying to make something different, you're making brownies, it's a different recipe. You know? And that's where that lack of porosity means you have to add that valley. So, you know, last year we took one of my dad's old NASCAR engines that had been sitting for 20 years. And it had been freshened up 2004. We put it back in the dyno. In 2004, it made 733 horsepower. We put it in the dyno last April, actually, and it made 732. So sitting for 20 years. By the way, the valve springs were never touched. So that's a myth, busted right there, right? Ran the engine, made 732. All right. All we're going to do is we're going to take out the pistons. We're going to go from that old school full round piston at a 043 top ring, 1/5 second, 3 millimeter oil, single grit finish, 400. It was old school. We put in a modern Ford side relief piston, same compression, same deck height. We went to a 0.7 millimeter, 0.7 millimeter, 2 millimeter ring set. We gas ported the ring versus gas porting the piston. And then we honed it just like this. This is the hone before we put it together. We put it in the dyno, we ran it, and it made 773 horsepower. That's 40 up. Just changing piston, rings, and hones, nothing else.
Yeah. In my experience, I've seen anywhere from an 8 to an 18 horsepower gain just by changing surface finish texture.
Yeah, it's that big.
Yeah.
That big.
Depending on your application, but I've seen it range anywhere from 8 to 18 horsepower.
So then, because we're curious, so what happens after 30 minutes? Just that initial run-in, those first few pulls. Take the engine back apart and remeasure it. And you can see all those peaks are removed, but all of our valley is still there. So the blow-by is awesome. Everything's running good. Engine's making power. It's super reliable because all those peaks are gone. Now the RK did come down about cut in half.
About half.
Again, back to why is it important not to take one extra?
Right.
Because if you lose all your RK, you're in trouble.
Yep.
Okay, but what happens when we run it for 3 hours? Simulator race, just keep pounding on it. Nothing. Right? If you establish the correct hone and you get it close, let the ring do that last little bit.
Yep.
Then it becomes consistent and it doesn't drop away. Whereas the old way, doing it, like I said, it'll be gone.
Yes. Well, yeah, if you think about that, if you had that 400 grit finish on your last slide there, and when we wore that little bit of peak off, there would have been nothing left.
It goes back to this. Right? Where's the one where it moves through? Yeah. It just does this.
Yeah. That's
boom. That's what it does. Because all that debris is staying in the cylinder.
right.
And now it's like an abrasive in the oil, and it keeps honing even you don't want it to.
Right.
So that's one reason why you don't want to leave it too rough or rough hone it that way and just let the ring do the work, because it doesn't know when to stop.
That's correct.
Until you do.
Right.
And that's not a good thing.
Yep.
So we talked about how much horsepower difference we can see. Let's take this out. So old school 280 grit finish and a methanol engine. So 410 sprint car, injected alcohol. That's how they did it in the old days, right?
Yes, sir.
Rough hone it, let the ring do all the work. Now let's go to a modern plateau finish. Look at all that valley. We're talking about a 95 RVK, but it's still flat on top though.
Yeah, you don't even see your little tail there.
No, so we got it nice and flat on top, tons of valley. Let's see how much difference it makes in vacuum, because in the old days, sprint car motors, you couldn't pull vacuum.
No, that's right.
You had to have big old giant breathers on the engines because they were just puking out all the time. So now, just changing the surface finish, that 280 grit finish, this is the vacuum. Remember, we want to go lower in vacuum, so down is good. Plateau finish is down here. That is 11 inches of vacuum versus 8 inches of vacuum. That's 3 inches of vacuum just on surface finish. Same piston, same ring, same cam, same manifold, everything the same. All we did was change the hone, and it was 3 inches of vacuum difference.
Yep. Yeah. I've seen on blown alcohol. I had the privilege of working on a blown alcohol car, and I know they've got all kinds of data recording going on, and we did that plateau hone on his Brad Anderson block, and going through the traps at 9,800 RPM, we were at 0.5% plus on the vacuum. Normally it's 5 pounds plus on the vacuum.
Yeah, it's pressure, not vacuum. Yeah,
That's right.
Yeah,
Exactly. It's pressure instead of vacuum.
yeah.
So we cut it in half by 4.5 pounds, or cut it more than half.
Yeah,
4.5
tons,
pounds.
yeah.
Yeah.
It's huge. But it's same like this, like 3 inches, pounds.
Right.
It just shows that when you give it the valley to hold the oil, then it can seal. And those both, crankcase pressure, crankcase vacuum are just different ways of measuring how effective the seal is. It's just proof in the pudding, right? You're actually from Missouri, so it is the show me state.
That's right.